Okay, let's just jump right into this explainer. Whenever you load a web page, send an email, or stream a movie, there's this massive, invisible infrastructure working tirelessly behind the scenes. Now, we constantly hear about IP addresses and Wi-Fi, right? But how does the raw data actually travel from your specific phone or laptop to the router sitting in your hallway? Well, today, we're focusing on the absolute bedrock of the TCP/IP model, the network access layer. It is the crucial final frontier where our digital data literally turns into physical reality.
To really wrap your head around this, think of it like the Postal Service. If IP handles the address on your package and TCP is the tracking system making sure everything arrives in the right order, this bottom layer, the network access layer, is the actual physical delivery truck moving your data down the street. It honestly doesn't care what the data is, its only job is getting it across the physical medium, whether that's a copper wire or invisible radio waves.
We've got a really clear roadmap for today. We'll start with defining the network access layer, break down MAC addresses, see how data gets packaged into frames, look at how network switches operate, and then tie it all together with some real-life local networking.
Right, let's kick things off with Section 1, the network access layer.
So what is it exactly? Well, if you look at the TCP/IP model as a stack, you've got your application layer at the top, the transport layer, the internet layer, and right down there at the very bottom sits the network access layer. It's completely responsible for managing how your device communicates within its own local area network, or LAN. We're talking about the Ethernet cables in your office, the Wi-Fi in your living room, the actual physical transmission of bits. Simply put, if this layer fails, absolutely nothing leaves your computer.
Now, you've got to understand the vital difference between logical and physical routing here. An IP address is logical. It's kind of like your zip code. It can change depending on where you're connected, and it routes your data across the global internet. But a MAC address, that's physical. It's permanent. It identifies your specific hardware right there on your local network. And down at the network access layer, it completely relies on these physical MAC addresses to get the job done locally.
Which brings us perfectly to Section 2, MAC addresses explained.
Every single MAC address out there is exactly 48 bits long. Think of it as a permanent, unique physical fingerprint that was burned into your network interface card at the factory. Honestly, it doesn't matter if you're using a smartphone, a smart TV, or a high-end gaming PC. If it connects to a network, it has one of these 48-bit hardware addresses, and it pretty much never changes.
You'll usually see those 48 bits written out in a hexadecimal format, looking a bit like this. It's broken down into 6 pairs of characters, and its entire purpose is to distinguish one specific machine from another on the exact same local network. So when your laptop talks to your home router, it's not actually using the IP address for that final jump. It's using this exact hex MAC address to make sure the data hits your machine and not your neighbor's phone.
Let's move right along to Section 3 and see how we actually package all this data into frames. Higher up in the network, the internet layer uses packets, and the transport layer uses segments. But down here, we use what's called a frame. Think of a frame as an incredibly sturdy shipping container. It takes the data handed down from above and wraps it up super tight in a format that your physical cables and Wi-Fi signals can actually understand and carry without spilling a single drop.
And these frames are highly structured. First, it needs to know who sent it, that's your source MAC address. Then, who's receiving it locally, your target MAC address. Tucked safely inside is the payload, which is your actual data. But the coolest part is the CRC, or cyclic redundancy check. This is a brilliant little mathematical check that runs at the end to make absolutely sure no bits were corrupted by electrical interference along the way. If a frame arrives scrambled, it just gets tossed out, and the upper layers will eventually ask for a fresh copy.
The best way to visualize this is like Russian nesting dolls. It's a process called encapsulation. You put a letter in an envelope, stick that in a mail bag, and load the bag into a shipping container. In your computer, your raw application data gets wrapped into a TCP segment, then wrapped into an IP packet, until it finally drops down to our network access layer where it's wrapped into a frame. From there, it's converted into raw physical ones and zeros to be blasted across the network.
Okay, Section 4, how network switches work. Let's look at who's actually directing all this local traffic.
To really appreciate modern networking, you've got to look at the past. We used to use these devices called hubs, and honestly, they were pretty dumb. If a hub received a frame, it just blindly shouted that data out to every single device plugged into it. It was incredibly slow and caused massive traffic jams. But switches? Switches are the intelligent traffic cops of the network access layer. They actually pay attention to those MAC addresses.
See, a switch actively reads the header of every incoming frame. It checks the target MAC address against its own internal MAC address table. This is basically a dynamic map it builds to remember exactly which device is plugged in to which physical port. Once it finds a match, it shoots the frame exclusively to that one correct port. It keeps congestion way down and makes local communication ridiculously fast.
Let's pull all this theory together in Section 5, Real-Life Local Networking.
Picture this. You're at work and you hit print on a document. Your computer knows the printer's logical IP address. But remember our rule. To physically send the data across the office network, we have to build a frame, and a frame absolutely requires a physical MAC address. So here's the mystery. If we only have the IP address, how on earth do we get the MAC address to finish building the frame?
Enter the hero of the day, ARP, or the Address Resolution Protocol. It bridges the gap between the internet layer and the network access layer. Whenever your computer knows an IP but is missing the MAC, it uses ARP to basically shout out to the whole local network, hey, whoever has this specific IP address, please reply with your MAC address right now. The printer hears it, realizes it's being called, and sends back its permanent physical MAC address. Boom, mystery solved.
So this entire 5-step dance happens in milliseconds every single time you hit print. Your PC checks the IP, ARP translates it to the printer's MAC, the PC packages your document into an Ethernet frame targeted at that exact MAC, the office switch reads the frame and routes it directly to the printer's port, and finally, the printer gets the raw bits and prints your page.
And as we wrap up, we really have to acknowledge just how physical this layer is. Once that frame is fully built, it has to become raw energy. Plugged into a copper Ethernet cable, those ones and zeros become tiny electrical signals. Using fiber optics, the data transforms into lightning-fast pulses of light. Sending a text over Wi-Fi, the network access layer is literally transforming that frame into radio waves broadcast straight through the air.
It really makes you appreciate all that unseen, heavy lifting happening inside your devices every single second. We obsess over the cloud and global IP routing, but absolutely all of it depends on this hardware-driven network access layer. Without MAC addresses, frames, and switches turning abstract data into physical signals, the internet as we know it simply wouldn't exist. So keep these foundational concepts fresh in your mind because this is exactly where the digital world crashes into the physical one.